This session is when the lights go out, hacking Cisco EnergyWise, and I'll turn it over to Matthias and Ayhan.
Thank you very much for the kind introduction, and of course, as always, for the possibility to present at Black Hat. My name is Matthias Luft. I'm presenting together with Ayhan Koca. I'm always happy when I get to talk about the technical topic at a conference. Basically, we're both working at EMW, which is a German-based security company. We're doing pen test, assessment, security consulting, all the fun stuff basically. Personally, I have to do most of the security management work, including a suit and a tie. So I'm always happy to talk about a technical topic. Speaking of presentations, it's actually Ayhan's first presentation at a bigger conference. Personally, I think Black Hat is a great start for something like that. But so also make sure to make this comfortable for him, ask him all the weird questions, make him pronounce funny English words. You get the idea, right? All right. We're talking about Cisco EnergyWise, which is an energy management protocol. And who of you has already heard of Cisco EnergyWise besides this presentation? Okay, that's probably like 10, 15 people. So that's what I assumed about the percentage that people would know about Cisco EnergyWise. We heard about Cisco EnergyWise 1 year ago. Brian brought it to our attention. Brian, say hi, thanks for that. And we had a closer look at the implementation in the protocol after that. Let me walk through the agenda really quick. Of course, we will have a short introduction. I think it should work. And give you an idea what Cisco EnergyWise actually is, how the general architecture looks like, what the features and functionalities are. And then we will have a closer look at the architecture and the protocol to give you a clear understanding how Cisco EnergyWise works. Because that's also what we had to do. We had to reverse engineer the whole protocol, since it's a Cisco proprietary protocol without any open specification or anything like that. So we had to reverse engineer the whole protocol, which is also one of the main topics of our talk. After that, apparently we got another introduction here. Pretty sure that was not the intention here. Basically, we will talk about attacks, controls, and conclusions after that. And we will show you how you can hijack a complete Cisco EnergyWise domain and what you can probably do about it if you're actually about to deploy Cisco EnergyWise in your environment. So, as for the actual introduction, not the one at the end, we're talking about energy management. I'm pretty sure all of you have heard about the huge energy consumption that IT equipment is responsible for in corporate environments. It's usually the main factor. It's a non-producing environment, and energy saving is a huge topic. As you can see, you get about like 60 million results in Google when you Google IT equipment, EnergyWise energy consumption. And it's already a topic in data center design and still in endpoints. I'm pretty sure you would be happy if your smartphone would live for like 4 or 5 days while you're actually using it. So energy management is a big deal, and of course the sales guys are thinking the same stuff, and I just collected some quotes from the energy websites, which I thought were quite a nice thing when talking to management, because when they read that you can save up to 35% in IT energy costs, this is a reason why EnergyWise will probably be deployed in some data centers. Also, an interesting thing I thought was when you Google green IT, you get roughly 3 million results. So basically the solution for the problem, huge energy consumption, has 3 million results, versus the problem has still 60 million results. So I thought it was like an interesting side fact. So the green data center thing is a big deal, and there actually have been quite some energy management protocols around. For example, smart homes offer the capabilities to power control devices. For example, when you leave your office in the evening and you have the Google Nest stuff installed, your heating system will come up and it will power down when you leave your home in the morning. And the embedded world is actually doing energy management protocols for quite a while. I also wasn't aware of this until I did the EnergyWise research. For example, HDMI Also includes the energy management protocol, which allows to power down other devices, or at least put it into standby. And also USB has like an embedded protocol to negotiate the power consumption of the device that is connected. Then again, in the actual IT world, in the more traditional IT world, we have certain IPMI implementations and BMCs that offer power management capabilities. So, for example, in the Fujitsu IRMC web interface, you get the capability to put a server to standby, to power it off, or also to measure the energy consumption of the device. So basically, energy management protocols that allow the gathering of usage data and maybe even powering down devices have been around for a while. However, Cisco EnergyWise is actually the first IP-based energy management protocol which can be deployed throughout the whole data center and not just in like some specific aspects like HDMI or for a certain type of server system that has the correct baseband controller, baseboard controller. So as I already mentioned, it's a proprietary protocol, and it provides support for power over Ethernet endpoints and for arbitrary endpoints that actually implement EnergyWise. So using EnergyWise, you can basically monitor your power usage throughout the data center by collecting all the power usage of all the different devices. And you can set and retrieve power levels of devices. So for example, you can find out whether a particular IP phone, access point, or any other device is currently in standby mode, powered off, or running. And you can also put it into standby or turn it off if it's necessary. So that's the basic functionality Cisco EnergyWise provides. And that's all of the functionality. I mean, when it comes to energy management, that's pretty much all you want to do. So, and speaking of retrieving and setting power levels, when you have a power over Ethernet device, of course the only thing EnergyWise is doing is, for example, powering down the Ethernet port, power-wise, not network-wise. And when we have an actual EnergyWise endpoint, the central management solution is directly communicating with that endpoint. We will have a closer look at that in a second. EnergyWise was also implemented in different phases, phase 1 and phase 2. Currently we are still in phase 2. There are different versions of EnergyWise, and most of the devices out there are in phase 2 and compatible with each other. So this was like the very, very high level introduction to Cisco EnergyWise. Now we will have a look at the actual architecture and how it works. We have an official Cisco picture here, and I'm surprised you can see it that clearly due to the dark background. The most important thing I want to take away from that picture is that we have 3 different, let's say, areas in here. I don't want to say layers because they aren't layers, but at the very bottom we have endpoints. Those are the devices that are managed by EnergyWise. Then we have the EnergyWise domain, which consists of network devices which are responsible for forwarding queries. And then we have the management application, or applications, depending on your setup. These are the management applications that monitor your power usage and allow to set power levels to devices. We also have that here in a better overview. And we will use those icons through the presentation to illustrate the EnergyWise architecture. First of all, the management applications, still that's pretty boring. It's a piece of software that is issuing management queries to the domain. And those management queries are processed by the domain members. Those domain members are all the network devices that are in your network and that are EnergyWise enabled. And those are responsible for forwarding all the queries through the network. We will see that on the next slide. And then we can have a variety of different endpoints, also called children. I will explain that later, which are managed by EnergyWise. They are also participating in the EnergyWise protocol, in the network protocol, but they are mainly managed. So, looking at the typical architecture, this is how it would look like. We have access layer switches, then we have a distribution layer here, the typical Cisco design, management application on the very left. And then we have the managed endpoints over here. I think I should also show it sometimes on this side, so I will switch over here for the next few minutes. And using this diagram, I will show you some of the typical protocol functionality in here. So the most interesting phase of the EnergyWise protocol is the neighbor discovery and the neighbor handshake. This is also something we will show in a second in our lab here. Neighbor discovery is performed in two ways. The first way is via UDP broadcasts, which are those purple packets, and those are exchanged on sent out on a regular basis on all EnergyWise enabled links. So on all network devices, you can enable for each switch port or for each network port whether EnergyWise is supposed to be enabled or not. When EnergyWise enabled devices receive such a neighbor discovery broadcast, they answer with a UDP unicast, which is directly addressed to the other system, and after this handshake is completed, they have become EnergyWise neighbors. We will show you that in a second. And of course, it does not only happen here, but on every link in the network that is somehow EnergyWise enabled. So there's a lot of traffic going on, in addition to the stuff that you already see on your network. So, an alternative neighbor discovery mode is via CDP. So CDP has an additional TLV that comprises EnergyWise data. And basically this is used within the EnergyWise domain between the different network devices. And the idea is the same. You get a neighbor announcement via CDP and answer with a UDP unicast packet, and then you become an EnergyWise neighbor. But this is not too relevant for our setup. We will show that to you in a second why not. So, once all the different EnergyWise devices in the network are discovered, you can start running queries on the network, for example, to collect power usage data or to power off or on a device. When you're doing this, you basically need a management application on the left. You can also issue commands on your switches, but if you actually want to use it, you surely want to have some kind of management application that provides you some kind of an interface to your EnergyWise domain. So when you're, for example, issuing a power collect query on your management interface, it sends out a TCP packet to all of its configured neighbors. So in the management application here, you usually statically configure your neighbors because you don't want to broadcast out your management queries like this happens in the next step. So when the query is actually processed by the EnergyWise domain, retrieving switches flood the query through the network. On all links they know there are EnergyWise neighbors sitting. So it's basically in the EnergyWise domain, it's a flooding-based protocol. So all of those devices retrieve those queries and they know, oh, I've got an EnergyWise endpoint sitting here. And from that point, they are using TCP unicast again to send that query to the corresponding endpoint. When the query does apply to an endpoint, I will explain in a second what apply means, then this endpoint responds again with UDP unicast to the to its parent, and this parent then directly sends the answer back to the management application. So there's no flooding on the way back. So the relevant part here is that we have TCP communication between the management application and the EnergyWise domain, and that we have a parent-child relationship between EnergyWise domain members and endpoints. So this IP phone is the child of this EnergyWise domain member, so they have a child-parent relationship. So basically all the domain members know which devices they have to address with queries. So that looked quite nice in a PowerPoint presentation, I hope, at least I hope so, and we will show that to you for a second in our lab here. For that we will switch over to our demo system. We got a very small setup here with 2 switches that we are using and some rather fancy demo device, which is basically LED light that is powered over Ethernet and which is turned off at the moment. So what we will do now is first, I think we need the switch.
Oh, okay, yeah.
Is first showing you the state, the EnergyWise state of the switch, and we are showing you the neighbors of the switch. So this switch has one neighbor at the moment, which is the upper switch, if you can see it. And actually, the discovery method was CDP in this case. And we can also see the EnergyWise children. And in this case, we only see the other switch here. We don't see any particular devices because the lower switch is just a member of the EnergyWise domain and does not have any direct children. If you would issue this command on the upper switch, we would see some direct children. All right, if I disconnect those switches from each other, this cable,
yeah.
and we...
Oh, no. So, yeah.
Ah, okay. Oh, we need this one.
This comes from...
So if we disconnect the switches and we do a clear neighbor so that there are no neighbors in the cache anymore. And you see our sniffer is running in the background. And if we connect those switches again, then we should see in a second in the sniffer, we see the interfaces coming up, and we see an EnergyWise broadcast packet that is sent out by the switch. Can you set a filter to EnergyWise packets? So we see that this packet is sent out. We don't see the answer yet.
Wait. The interface is not.
Okay, we might need to give that a second. Or maybe, can you do a show neighbor? Maybe they did it via CDP again. Ah. Okay. We somehow missed the handshake here, but we see the discovery packet of the switch, and we see that they established a neighbor relationship between each other. Of course, they keep broadcasting to find additional neighbors, but at this very moment, we can already issue EnergyWise commands throughout the domain. And that's what we're going to do now, because we want to turn on this very device here via EnergyWise. So at the moment, we're connected to the lower switch, and using EnergyWise, we're going to turn on the top switch and the small light that's sitting on top of it. So doing this, you can issue on this switch directly an EnergyWise query command. Please don't send it yet, so I can explain it for a second because you send it out. So EnergyWise query, I think that's rather obvious. Then we have an importance of 75. We will discuss importance in a second, but each device has an importance assigned. So you can, for example, power off all non-mission critical devices in a network. And we address it by the name troopers and set the EnergyWise level to 10. And if we issue this query, then it takes a second and the light turns on. So that's basically what you can do via EnergyWise. Okay. So that's the basic protocol functionally. Oh, what you could also do is like issue a short usage query. So can you show the power consumption of this device? So we're basically doing the same thing, but we're not using a set query then. We're going to use a collect query of all the devices out there. So we're using a wildcard, and we're collecting the usage. And then in a second, we should see the power usage of those devices, and we can see that this small LED light consumes 2.6, how do I pronounce it? Watts? Watts? of power. So that's the basic functionality of the EnergyWise protocol and basically all you can do with it. So, so considering that this usually would not only be a little LED light, but could also be your servers or your phones or your air conditioning or even surveillance systems, it becomes rather obvious that functionality like this to turn off devices is also security critical. Of course, you can only target availability of devices and not own a server over that, but still it's relevant. So, before we go into more detail, I want to point out some details of the EnergyWise protocols, which are called EnergyWise Attributes. We already saw the importance. Each endpoint has an assigned importance, which ranges from 0 to 100. So you can, for example, turn off all non-mission critical devices in case of a power outage or something like that. Then you can assign roles and keywords to endpoints, for example, to address all phones throughout the network, or IP cameras, or all web servers, or application servers. So that's basically like a grouping that you can do here. Roles and keywords are somewhat similar. I did not really understand the complete difference between those, so you can basically use them in the same way to establish some kind of grouping. Then we already talked about the level, which is the energy level that you are setting to a device, and every endpoint has a name, so you can also directly address different endpoints. Different EnergyWise levels look like that. They range from 10, which is fully functional, to 0 off, and then you have sleep hibernate, or you can put them in a power saving state, or stuff like that. So, now that we had an idea of the overall EnergyWise architecture, we need to see, is it really relevant? I mean, there are lots of protocols out there that you could analyze and that are probably broken, but it might not make a big difference for the world. So we had a look at the EnergyWise usage out in the world there, and I already mentioned smart homes and smart cities. I'm pretty sure energy management protocols will gain enormous importance with all the home automation systems and stuff. So for example, for the smart buildings, there are already like 15,000 discovered building automating systems alone in the US. This is based on the numbers are based on some research from a German researcher, Stefan Menzel. And in a talk he mentioned they found like 400,000 devices at all exposed to the internet and like 15,000 confirmed building automating systems in the US alone. So probably some of those will also be relevant for energy management protocols. And what I just heard recently, 2 of the five biggest companies in Germany are thinking at this very moment. Okay, I mean, it's probably rather late in Germany at the moment, but they are thinking about actually deploying EnergyWise in their data centers for saving energy. So EnergyWise is actually a thing out there. And then what we saw by accident when we were riding a German train, Ayhan was actually working on EnergyWise and had his sniffer running, and we saw in this very network EnergyWise packet that we were able to sniff. So the interesting fact here is that every Lenovo notebook that has like the default set of Lenovo tools installed has an EnergyWise agent included that can be used to power down the device. Unfortunately, a little pop-up pops up that asks you whether you actually want to power down the device. So it's not that easy. But Lenovo notebooks in the default installation ship with an EnergyWise agent installed and activated. So there's also some real-world stuff out there. Then we performed an internet-wide scan for EnergyWise devices. Pretty sure Mike, who is presenting after us on the state on internet scanning, would be pretty mad at us at this point. Sorry, Mike, not sure whether he's around. The problem with that is that it's really difficult to do like an EnergyWise discovery protocol, because in every packet, an HMAC must be included and further device information must be included, like a sequence number that you need to use. So it's not possible to just send out a default packet and get an EnergyWise answer back to actually determine whether there is an EnergyWise implementation running on that device. So that makes it rather difficult. So what we did is search for port 43440, which is the default EnergyWise port, and then perform a host discovery to check whether it's a Cisco device, because that would be sufficiently a sufficient indicator that actually EnergyWise is running on that device. Unfortunately, this approach is incredibly slow performing the host discovery. So far, we found 1.7 million hosts with TCP 43440 open. 5% of those, the host discovery, the banner grabbing is already performed, and at least we found 4 identified Cisco devices in the internet with this TCP port open. These are not very impressive numbers at the moment, but most likely EnergyWise is already running on some internet exposed systems. But given that EnergyWise is mainly used within the data center, it's probably a good thing that we did not find a lot of devices at first try. So, now that we know that EnergyWise is relevant and about to be deployed in actual data center environments, we're going to have a closer look at the protocol details and how we did the reverse engineering, and this is where Ayhan comes into play.
Hi.
Can you
Good.
Okay.
I will explain the EnergyWise protocol in more detail and show you the approach, how we reverse engineer the protocol. And first we used this lab to generate different EnergyWise packets and analyze them to get a first understanding of how EnergyWise works and how they communicate and how they get. So this lab is too complex for our demonstration now. Because of that, we have a little bit more simple setup, which is based on 2 domain members, which are these switches here. The one domain member has this fancy LED light as a child. And also we have a notebook connected to the endpoint, which has 2 interfaces. The first interface is Sniffer to get the packets and to see how EnergyWise communicates. And the other interface is the attacker, which are able to own the domain. So for the attack, we wouldn't need 2 domain members, but to get an understanding of how EnergyWise regularly works and how they communicate, we have the second domain member to see how they communicate and how they have the packet exchanges. So our approach to reverse engineer the EnergyWise protocol was to identify first the text strings in the packet. After that, we try to identify environmental dependencies like IP addresses, MAC addresses, date, timestamps. After that, we try to find the Cisco parameters. To get these, we generate a lot of different EnergyWise packets with different parameters. After that, we compare the packets and identify the parameters like the importance, the name, the level. So we find these values. As a last, we try to find length fields, also meta fields, fields that describe other fields, like a length which describe the length of the other field. So I will show you basically this on an example how we do that. So first we find the text strings, which you can see here is the text string is the model number of the switch. The second string is the name of the domain. So after that, we try to find, for example, the IP address, which is there. And nearby the IP address, we have the port number of EnergyWise. The A9D0 is the port number of EnergyWise. So after that, we try to find some Cisco EnergyWise parameters, which in this case the importance of 100 is 64 in hex. So after that we find length fields. So this length field this is the length of the packet content. So this field gives us the ability to extract the header from the data. So now we are able to get the header of the EnergyWise packet. This this header is if we use UDP, and we have also the package for TCP. We can see the TCP packet has a UUID instead of EnergyWise ID, because the UDP packets is only communicated in the end domain, EnergyWise domain, which domain member says usually model number, a version ID, and the system serial number. But EnergyWise over TCP is also communicated over our management tools or over software, and they normally has no model number. Because of that, they have a UUID to identify these uniquely in the domain. So I will show you in more detail
I will switch to Wireshark for a second again, where we have another packet open. I hope that is big enough for you.
So, like Matthias mentioned before, we didn't get all fields, but the most relevant fields for the understanding of EnergyWise I will show you. So first, we have the hash, which is calculated with the packet, with the data of the packet, and is used to authenticate the packets between the domain members. After that, we have the sequence number. The sequence number is used to align the packets between the domain members. So, for example, if a router or endpoint or switch sends a broadcast message with the sequence number 1, 2, 3, 4, the responding domain member to this answer should have to use the same sequence number 1, 2, 3, 4 in his answer. So after that, we have the EnergyWise ID. The EnergyWise ID, in this case, as a switch, is used to uniquely identify the domain member in the entire EnergyWise domain. So we have the message types. Also requests are 0100, and the responses are 01FF. After that, we have the importance which we show in the query. So we have the length of the TLV table, which describes the length of the data section of the packet. Then we have the number of TLVs. In our case, we have 8 TLVs in the data, which we can see. Yeah, we go it. So the first TLV is the EnergyWise domain, which only consists the EnergyWise name of the domain. In our case, it is a switch domain. The second TLV is the EnergyWise reply to TLV, which consists the IP address and the port number of the sender. So the second, or the next TLV is the EnergyWise name, which is used in the query to address the EnergyWise query. In our case, this is a wildcard to address all EnergyWise members. The last value, TLV, is the level value, which is used to turn devices off or on. In our case, it's a 0, which means the LED light would turn off. So.
All right. Now that we got a better understanding of the EnergyWise protocol, I will highlight some of the protocol details that we will need later on. For example, Ayhan mentioned that there is like a hash data in every packet, which is basically an HMAC. This HMAC is used to authenticate domain members against each other, and it's based on a shared secret. You probably already see where this is going, but give me a few seconds to get there. There are actually 3 different secrets in an EnergyWise domain. There's the management secret, which is used for the communication between management applications and domain members. Then we have the domain secret, apparently used within the domain, and we have the endpoint secret, which is used for communication between domain members or parents to their children. So this is basically what we need to know about the HMAC, the authentication at this point. Ayhan already mentioned the sequence number, that those must match in communication to actually align packets with each other. This is also something we did not completely find out yet, because it's really funny behavior. You also saw that we did not completely identify all TLVs, because they just don't seem to be used for anything so far, so we can hijack the EnergyWise domain also without changing those TLVs. And the sequence number is really funny, because for some queries or processes it actually needs to match. Then there are queries that are mentioning in the debug output, oh, sequence number is not matching, but the query is still carried out and answered. And then there are some queries that just do not finish when the sequence number is not matching. So that's really interesting behavior here. And then we have the UUID versus the EnergyWise ID, which also means that the HMAC is calculated in a different way when we're talking about management secrets and endpoint secrets. So probably what you've all been waiting for. How are we hacking this now? Sorry, I think we need a rather good protocol understanding to also understand the attacks. But let's look what we did. First of all, as we saw in Wireshark, EnergyWise is a plain text protocol, so there is no encryption applied. So as soon as you're in a position to sniff traffic, you can also sniff power usage data. I don't think this is the most confidential data ever, but there might maybe some billing related issues or something like that. So this is not listed as a detailed vulnerability in the slides, but of course it's a clear text protocol, so if you can sniff it, you can also sniff energy consumptions and queries that are performed. What of course comes to mind when looking at nicely defined fields like that is fuzzing those, which we did of course, and we also had some results. This is our Dizzy script that was implemented for Dizzy, which is the ENW fuzzing solution developed by Daniel, which is available here. And long story short, of course the device crashed when we found a certain query. And this means the switch crashes hard, and you have to hard reset it to make it functional again. So the query that needs to be sent has the 10th byte in the header set to 15, hex 15, while the valid value is hex 10. The funny thing is, we did not really find out what this byte is used for so far. So we only saw values defaulting to 10. So also there might be some hidden EnergyWise functionality that we did not discover yet. The advisory for this crash came out yesterday, and I hope you understand that this will be the last demo we are doing, because otherwise we would have to reboot the switch, and crashing a switch that you might use in the next demo is probably not such a good idea. So, but this is a screenshot from the crash, and of course we will demonstrate that at the end of the presentation. Then, when thinking of HMAC-based authentication, a very first naive approach comes to mind, which is a replay attack. If you're in the position to sniff an EnergyWise query, you might as well just replay it, which is especially interesting when you're turning off devices. For example, every evening, 9 p.m., all your office phones are turned off, and you sniff the packet that is turning off those phones at 9 p.m., you might as well send this packet at 9 a.m. in the morning and get everybody a late start to the day, which might be desirable for some persons. So this actually worked, but there is a very simple mitigation to that. This is a Cisco config parameter, which is either a shared secret or an NTP shared secret. So when you use NTP shared secret, an NTP timestamp is included in the HMAC calculation. So this is rather a small finding because it's easy to mitigate, but we still wanted to mention it to illustrate the relevance of using NTP shared secret instead of shared secret. So now that I already talked about the shared secret stuff and the HMAC, we will show you how the HMAC is calculated. Luckily, Cisco provides a small demo application which is called EnergyWise Test App.exe, and out of that we could extract the algorithm that was used to calculate the HMAC. So the HMAC is calculated based on the shared secret and, in case of TCP, the UUID that is sent in the packet. A hash value of these two values results in the key, and this key is then used together with the data to calculate the actual HMAC. So this is the HMAC algorithm, and as you might see at this point, we are able to perform brute force attacks, offline brute force attacks on HMACs to crack the shared domain secret and be able to participate in the domain. So this is the actually relevant information here. And for UDP, the nice thing is we don't even have the UUID, so the cracking process comes down to one hash calculation, which makes it even faster. And the basic idea is the same. We have the shared secret and we have the data. Unfortunately, all the relevant data is included in the HMAC, so you cannot tamper with IP address or something like that. So that is done right at this point. So, how can we use that? There are basically 3 different steps that we have to perform. The first step is sniffing a packet that contains an HMAC. Then we need to crack the secret, which is now easily doable now that we know the algorithm, and then hijack the domain, of course, by sending fake EnergyWise packets. So the first step, sniff the secret, is unfortunately always possible when you are in the same segment with an EnergyWise enabled endpoint. Let me illustrate it for a second. The neighbor discovery process always uses the domain shared secret to discover new neighbors. And as I showed earlier, those messages are sent out on all links, which includes all endpoint links. So if you're in the same segment with an EnergyWise enabled device, you will get the UDP broadcast message including an HMAC. So getting the HMAC is really easily possible in an EnergyWise domain. That is the sad story. Luckily, we can mitigate the impact of this a little bit by using the management secret, the domain secret, and the endpoint secret, and not setting all of those to the same password. But I don't need to tell that to you, right? We will come back to that when we're talking about mitigating controls. So sniffing, unfortunately, is always possible. Also of the domain secret, which is a really relevant secret. So, crack the secret. One thing that came to my mind is that once you crack the secret, it's probably valid for a very long time. Because the secrets you configure, they must be used throughout the whole EnergyWise domain that includes all the different devices. So I leave it up to your fantasy how often these passwords are changed when you think of your SNMP secrets in your environment, or your OSPF secrets or something like that. That probably won't be too often. And then again, SHA-1 is used as a hash algorithm, and the cracking speeds for those are really high. I won't provide any numbers. The guys from Passwords, somewhere around in Vegas, will probably release some nice numbers soon. So the cracking process is really fast. So cracking the secret is also easily possible. So the last step that we need to do, now that we know the secret, is we need a tool set to actually hijack the domain, to create fake EnergyWise packets, which was not fun to implement, but I hope the demo will be working, and I think that's the relevant part. All right. I will switch over to our demo notebook again. You ready, Ayhan?
Yeah.
I will leave that up to you. So the first step that we need to do is to crack the shared secret. And to do this, we will use the network dump that we created earlier. And I actually have an idea why we did not see the neighbor handshake earlier, because we probably used the wrong interface, but I'm not sure. But it also shows that it's easily possible to sniff the value. Our current cracking script is implemented in Python, which is performance-wise horrible, I know, but we're currently talking to the Hashcat developers, so hopefully there will be an EnergyWise module soon, but more on that later. And we're supplying a PCAP file that contains the HMAC, because that's the easiest way, because we also need to use the data that is used for the HMAC in order to crack the shared secret. You can simply export that from Wireshark once you sniff the packet, and then put it here. Then we're supplying a word list, and you won't be too surprised if you're running this now that it goes really fast. Go ahead. And of course, we found our secret. Sorry, it was in our word list. I don't think you wanted to wait for some hours here until the brute forcing process was finished. And of course, it's a weird German word. That's what all of you are expecting when Germans are giving presentations, right? So it's basically secret. That is our domain shared secret. So once we know the shared secret, it's basically game over. Now we are able to send out fake EnergyWise queries, and in order to do that, we first need to become an EnergyWise neighbor to be part of the EnergyWise domain. To do this, I think we will disconnect the switches so we don't have any interference here. Then we will clear out the neighbors. So this is still the old switch in there. We will clear that out. And the top switch, which is basically the victim switch at the moment, does not have any neighbors. Can you do the show neighbors again, please? So no neighbors at the moment. So when we're performing our fake neighbor handshake now, we're supplying the IP address we're targeting with our shared secret, with our shared domain secret. And if you don't minimize the window, we should see that we have become an EnergyWise neighbor of this device over here. So now that we are an EnergyWise neighbor, we are able to perform queries throughout the EnergyWise domain. And that's what we're going to do to turn off this device. So we also implemented a short script, which is somewhere in his history, or not, which is query off. See the usage, it's again the IP address that we need and the shared secret. Once we got the keyboard figured out, we will be running in a second. All right. And the light goes off. So these were, thank you. Yeah, it was, Ayhan probably hated me when I came up with additional questions. And can you implement this and that? So the scripts now seem to work really smoothly, but it was quite some effort, so thanks a lot. Of course, we can turn it back on again because we don't want to miss our shiny little light. But that's just the finishing touches. So basically what we are able to do, as soon as we've been able to sniff the EnergyWise secret, turning it on somehow takes a second, but it will turn on rather soon. Or not, we will see. As soon as we sniff the secret, we can crack the secret, and then we can hijack the EnergyWise domain, and of course we will publish all of those tools. So in case you have to use it in a penetration test, you will be all equipped. Okay, I will switch back to the presentation at this point, because that is basically the relevant vulnerabilities that we discovered in the protocol. So we are able to compromise servers by means of availability. And when we are thinking about the EnergyWise architecture, the very best case, which is not very likely in my opinion and experience, is that we are not able to shut any server down because the EnergyWise port is filtered in a local packet filter and restricted to domain members. The most likely case, at least, is that you're able to shut down all the servers in your network segment. Because usually, if the EnergyWise port is filtered at all, it usually happens on the segment boundary. So at least you will be able to turn off all the endpoints in your segment that you're currently in. And the worst case, of course, shut down all EnergyWise endpoints in the data center, which from our experience is also not too unlikely, considering the usual state of firewall rules and how well organized they are. So, another problem, of course, with the shared secret approaches, but this is also nothing new, is devices sold on eBay. We had that at least 7 to 10 times over the last 10 years when we bought devices on eBay, probably like those, and there was still a config included, including all passwords. One time we even got a switch with one of our customers, which we knew from an assessment and the strings that were included, so we contacted them and let them know someone sold one of your switches, including your configuration in there. So this is also particularly ugly because, as I said, the shared secret needs to be configured on every single device in your EnergyWise domain. So changing those shared secrets is really difficult and painful. So you have the same organizational problems as with any pre-shared key-based protocol. So that's nothing new, just wanted to illustrate it. When we're talking about controls, there are some obvious ones that I don't need to tell you. Use strong shared secrets. Make use of the different secrets, the management secret, the domain secret, and the endpoint secret, to have some segregation in there. So if you're able to hijack an endpoint secret, so you won't be able to hijack the domain, for example. Same for the management secret and stuff like that. So use different secrets, and of course use the NTP shared secret. There's also a nice hint in the EnergyWise design guide that states, please make sure that your clocks do not drift more than 30 seconds, because otherwise EnergyWise won't work. I leave it up to you to figure out the window of replay attacks that you have left. Then some specific EnergyWise controls that we can implement is, of course, purge configurations during decommissioning. That's not EnergyWise related. I just wanted to mention it for completeness sake. And there are some actual EnergyWise hardening options that you can do. When you're using EnergyWise just for power monitoring and not setting power levels, you can actually disable set queries on the devices so that it won't be able to set power levels, turn it off or on, but just to monitor data. So this is also an actual control that you should implement. Then, of course, actual crypto should be used. Talking of certificates and auto-enrollment, SCEP and all that stuff, I won't go into detail in that. Of course, it would be nicer if the protocol would have some actual crypto support that you could use with your corporate PKI. I'm pretty sure you're all aware of all the operational problems and challenges that come with that. It would be nice, not sure whether it's too realistic, but of course, for a protocol designed in 2013, it would be a nice thing to have, at least optional. And then, my favorite part, segmentation. This is where you can actually do a lot. Whenever it's possible, you should use different EnergyWise domains. The problem with that is every device can only be a member of one EnergyWise domain. This is not a problem for endpoints, but of course it is for the domain members. Because then you have like a physical constraint to an EnergyWise domain. And this is a problem when you're taking your IP phone with you from your old desk to a new desk, which is in a different building. So let's say the different buildings have different EnergyWise domains. So you can't use your IP phone in the different building because it doesn't have the correct secret with it. So segmentation on an EnergyWise domain level is difficult. If you can do it, you should do it in any case, because that keeps the impact of a leaked secret lower and restricted to a certain EnergyWise domain. However, certain operational problems with that. Then the classical old segmentation and filtering approach, which we are still big fans of. Restrict EnergyWise ports to the local subnet. So for example, don't block EnergyWise communication throughout the network on all access ports. No client should have the need to communicate with the EnergyWise domain member on port 43440. They only need to send answers. They don't need to be able to send actual queries out. So you should filter at least on subnet borders and blacklist EnergyWise ports. We're currently talking with Cisco about that, whether it's possible to include it in this design guide. Just to illustrate that for a second. The problem with the sniffing is that the broadcasting happens on every EnergyWise enabled link. So you can't do any filtering about that. Because the endpoints and the domain members rely on this mechanism to become neighbors. So, but what you can do is block port, the EnergyWise port that you configured on all the access devices. So your endpoints won't be able to send out EnergyWise queries to the domain. That's definitely possible because that's not necessary for the protocol. They only need to answer queries. And this will remove a lot of the domain hijacking problems and at least restrict EnergyWise related attacks to the local subnet. So I think that's also the case. We of course have some future work to do. For example, we want to port the tools to Loki, which is a network attack framework that also Daniel implemented. We want to analyze a few missing protocol details. And of course write a more efficient cracker. As I mentioned, we're already in contact with the Hashcat developers. So if we are lucky, there will be Hashcat modules to crack EnergyWise secrets very soon. That would be amazing. So we don't have to write yet another cracker. And of course we want to publish like more detailed hardening information than what I just told you now about. Or maybe even include this in the Cisco EnergyWise guide, which would be a really nice thing to do. All right. I hope you all got a good understanding of Cisco EnergyWise, what its features are and what you can do with it. Basically shut down your whole data center if you mess up the configuration. Use wrong, weak secrets. Don't block the EnergyWise ports and all that stuff. We also saw that probably appreciate key-based security is not appropriate anymore for infrastructure protocols in 2014 because of all the problems that are associated with it. And good old principles still apply. Segment your network, really think about your isolation and filtering model. And if someone did not apply this basic principle to his or her network, you now got the tool set to assess EnergyWise domains if you find that somewhere. And you get probably some arguments if someone wants to deploy EnergyWise in your network. All right, that's it from our side. Thank you very much for your time. That was quite good, I guess. I think we have 3 minutes for questions. Any question? Yeah, okay, coffee break. You
mentioned that Lenovo
yeah.
the agent by default. Have you looked at any other default agent installs?
So the question was whether there is only the Lenovo default install. We are only aware of the Lenovo agents. There are no other devices out there at the moment implementing EnergyWise. There are some management applications, but endpoint-wise, Lenovo is the only one. And we did not have that in the slide, but the default secret is EW_test secret. So just to have that mentioned. Yes.
Is there any implementation of access maybe looking with the host that are next to that?
Sorry, I didn't completely understand you.
If you go into a switch with another device that's taking over the ID of an existing.
You are actually able to override neighbor relationships. That actually is possible. This is something we experienced during preparations. We still have to look deeper into that, but that's possible, yes. Yeah. Sorry?
Can there be more than one controller? Like
Management applications or? Yes. Basically everybody is able to send out queries that knows the secrets. So there is no like IP-based restriction for that. Yeah, if you know the secret, of course. If it's a valid packet, you are able to send out queries, just like we did. Sorry? Because some queries don't really check the sequence number. That was the thing I mentioned, which is really weird about the sequence number. So if you replay the correct packet, which actually is the turn off packet, you cannot turn on with a wrong secret number, but you can turn off with a wrong secret number. that actually works. Yeah?
You can turn it on and off, and can you also manipulate voltage?
That is not possible, I think. Is it? Sorry? That is what the device does to it. If you have a power over Ethernet device, it's basically on or off. But everything that is associated with that level depends on the EnergyWise implementation. So there is an agent sitting, and that agent knows what to do with the level 1 to 10. So that depends on like the endpoint. You cannot send, basically blow up the device. That's not possible. To consume that much power, that's not possible.
We can show the question.
Oh, we did not show the denial of service, but I think most of the people already left. Who wants to see the denial of crash it? Okay. I mean, I can switch over to the demo notebook again, but it's not too impressive. It's just another Python script running, and then the switch turns off. But while we're doing this, any other questions? Doesn't seem the case. Everybody wants to see the crash, and then we're good. So we have to switch here. We got our crashing packet over here. Now that we're sending this, we should see that it's crashing soon, or not. I mean, it's really bad. You reminded me of the crash, and now it's not crashing. Okay, apparently it doesn't seem to work at the moment, so sorry for that. I mean, it's always easy to say yesterday it crashed. And there's a confirmed Cisco advisory about that, so we got at least that. If there are no more questions, I would like to thank you for your time, and we'll be around for further questions. Thank you.